So previous lesson, we have discussed the formalism of quantum mechanics. I introduced you the postulates. We will continue in the first maybe 1 hour or maybe 1 hour and a half, depending on how many questions you have. We will discuss the extension of the formalism. I'll present to you the formal solution of the Schrodinger equation, and then later I will use that to explain a little bit of the history of quantum mechanics, especially what exactly did Heisenberg do and what is his point of view on quantum mechanics. Heisenberg, as you know from the history, he invented quantum mechanics together with Schrödinger, but the two languages that both of them used were a little bit different. They are connected because eventually the physics is the same physics. So there are two formalisms, one of Heisenberg, one of Schrödinger. In reality, most people use most of the time the Schrödinger description. That's why it's more useful or famous. But they are equivalent, and some people like to use the Heisenberg formalism. Of course, you know this also from classical mechanics. For example, you have Newton's equations of motion, and later Lagrangian and Hamilton-Jacobi and all these things. You know that essentially, bottom line, everything is the same. The difference is that in classical mechanics, Newton is everything, and the rest is extension. And here, two people, more or less at the same time, gave the same formalism in parallel. Eventually, one of them became more popular, more easy to use his formalism. But that means Schrödinger won in some sense. But eventually, both of them are great scientists. One of them actually was a Nazi. Maybe I should not teach him here, but there's an interesting stories about this. But let us leave politics and philosophy. Heisenberg. Schrödinger actually ran away from Austria to Ireland. He was a very interesting guy because he had two wives. So he was a bit different than most people in physics. Heisenberg was part of the Nazis knew that the Americans are building some big bomb, but luckily they believed somehow that this is Jewish magic because Einstein was behind the atomic bomb, I mean. So they didn't, we're not so sure, and then they asked Heisenberg to do something like Project Manhattan. This project did not advance so much, and after the war, Heisenberg claimed that he deliberately did not want to advance this. No one really knows, did he not advance it out of real ideology, or he was not willing to cooperate with the Nazis, or maybe he was not able. It was very convenient for him to say after the war, you know, I didn't really try to make an atom bomb. We don't know if I think the historians are debating. That's why Heisenberg, he got the Nobel Prize eventually, but it took a long time. I think only in the 1970s he got the Nobel Prize, something like that. Anyway, these are nice stories, but let us go to the more important part, and that is we want to solve the formal solution of the Schrodinger equation. Formal solution of the Schrodinger equation. Well, you know, formal, most of the time I don't like the word formal. Formal means it's not really practical, but I can solve the Schrodinger equation. And this a little bit helps us to understand what is going on, or just gives you some point of view. So we are going to work with Hamiltonian p squared only for one particle over 2m plus v of x. So we have a time-independent Schrodinger equation, but this can be made much more general. And also, I work in one dimension, but just for simplicity. We know what is the Schrodinger equation. We know that Schrodinger equation is this thing. Now I'm using the bracket notation of Dirac. I act with the Hamiltonian on the state function, and I have IH psi dot. This is the Schrodinger equation. of course, at the beginning of the year, we had this H, like say particle in a box or harmonic oscillator, different examples. So this was some function of X, but later on we saw that H, for example, for the harmonic oscillator can be represented by a matrix. And if you have, let's say, a few state system, let's say a system with 1, 2, 3, or 4 states, this Hamiltonian generally will be some matrix given by the size of the system. You will have many exercises on this. So you can view this in a kind of abstract way. What exactly is this Hamiltonian as you wish, because actually this is in a Hilbert space. Now we know how to solve this equation. This is nothing new. I have the first thing I need to do is I need to find the Eigen values and the Eigen states using the time-independent Schrodinger equation. So I have H, phi n. These are the Eigen energies, phi n. Okay, it's very easy for me to write it on the blackboard. In practice, it can be very difficult to find these energies and these wave functions, these stationary solutions. But we now use formal solutions. Let us assume that we know what these are. And you can choose one example that you know already as a particular case. So we know what is the solution, of course. This is psi, and that is given by this expansion. Here I'm using the fact that I'm working in one dimension, so I have only one quantum number. This is n. And so n is some integer, let's say starts from either from 0 to infinity, or 0 or 1 to infinity, or let's say 1 to 5 if the number of states is limited, whatever, but some integer. It's one-dimensional, so I have only one quantum number, and I need to sum over this guy. So I write it as n. I don't write the number because this depends on the dimension of this Hamiltonian, essentially. Then you know the solution. It is given by C n e to the minus e n t over h bar phi n. And this was already in the classroom. We showed this at the beginning of the semester. And we used maybe a slightly different notation, but this is exactly the same. You can just plug this in here and see that this is a solution, because so I'm not going to prove this. I'm assuming that you know what this is. You know what are these CNs? Do you remember what are these CNs? These are determined by what? Okay, from the initial condition. So I can take t equals 0. Then this guy will go because e to the minus 0 is 1. And then these guys are orthogonal to one another, and essentially Cn in this language is simply phi n psi at time t equal 0. So this is psi depending on time. This is our Cn, and all this is known. Now I want to give you a different way to write this, essentially. So, I mean, this guy we used to write in the position representation like this, but it doesn't have to be this. Psi x equals 0 dx. This is more general. This was what we had in the beginning of the classroom. Okay, so we use here the fact that this is a Hilbert space, so these phi n's are forming a complete basis. So I can expand any initial condition with this series. So this is a complete set. So this is what I'm using here. And this is fine. So the initial condition, I'll just write it down, was psi 0 sum over Cn phi n. So now I want to point out to you now something slightly new. I want to show you some identity. And I'll write down the identity, and then we will discuss it and what it means. So an identity which is the following thing. I take an exponential of minus I h t over h bar and operate on phi n. This I claim, and soon we will prove, that this guy is equal to exponential minus I En. So En is the energy associated with this Eigen particular angular state, with a particular quantum number, t over h bar phi n. What you have here on the right-hand side may be, on the left-hand side may be new for you, because what do we have here? This is an exponential of an operator h. So I don't know if we already discussed functions of operators, but what you have here is an example, a very particular example of a function of an operator. Soon I'll explain a bit more. But this function of an operator, when it acts on this particular states, gives you back a simple number, and it's just this phase given here, the corresponding energy. So what is this object? What is an exponential of an operator? In this case, h. So in generally speaking, this is a general definition of f of some operator a. What is this? How will we define it? What does it mean? What you need to do is the following thing. This is a definition. You take the function, which you know, for example, exponential, and you expand it in a Taylor series around 0. And then, instead of the argument inside this function, you put in the operator. So the formal thing here, I'll just write the first terms. So I expand this function around a. This means actually that it is multiplied by the unit operator. So if a is a matrix, here I have the unit operator, but this is f0. Then I have the first derivative at 0 times a. And then I have the second derivative at 0 times a squared over 2. And then I have an infinite number of Taylor expansion. That means that the function f is assumed analytical. Analytical functions are functions that you can Taylor expand around the 0. Yeah. So if you have a function, let's say for example, cosine x when x is between -2 to +2, but then it's some other function exponential of 22x from on our other end. That is not an analytical function, because if you expand the cosine around the 0, you will not get the other part. So I'm just talking about smooth functions, nice functions. Exponential is an example. So this is just the definition, and definitions we write with 3 lines. This is the meaning. Any function you see, any function of operator, you need to do this to get this definition. So in this case, so in our case, what is exponential of minus I ht over h bar? H bar is becoming very annoying that I need to carry it. I would like to take it to 1, but maybe you don't like that. So let us leave it. So what is this guy? Well, I need to remember what is the Taylor expansion of the exponential, but I hope all of you know or remember, and if you don't, you should know this. So the first term is simply 1, which means 1 that will, remember all this thing is an operator. So this 1, let's say acting on a state function, will give you the state function back. It is not 1 a number, it is 1 an operator. For example, in a matrix form, what is this guy? It's a matrix with diagonal term. By the way, let's say this matrix H is has size 20 by 20. What is this? What is this exponential? It's some? It's another matrix whose size is 20 by 20. So the size of the matrix H will give you the size of this unitary operator. For example, for the harmonic oscillator, what is the size of H? It's infinity by infinity if you write it as a matrix. So this nice object is a matrix which is infinity by infinity. Is it easy to find this thing? For example, for the harmonic oscillator? The answer is rather it is easy, because what is H? It is diagonal. when you write it as a matrix. And then you can expand, and then if you have a h to some power 1, a diagonal matrix to the power 1 is again a diagonal matrix to the power 2 is a diagonal matrix. So in short, when h is represented, for example, as a matrix which is diagonal, then this guy is really easy. If it's not diagonal, then it can be, generally speaking, is difficult, but essentially all of quantum mechanics is find the Hamiltonian, bring it into a basis where h is diagonal, and then this propagator, this is called a propagator, you'll see why soon, you can calculate it. But okay, let us just do this now for the sake of generality. So the first term in the expansion is this guy, and then you have 1 over 2 factorial from the expansion, and here you have minus I h t over h bar to the power 2. You have many, many terms, but I can, of course, write this as sum of k. K is the index which will describe the Taylor series, minus I h t over h bar to the power k, k factorial. Why k factorial? This is the expansion of the exponential. This thing, I wrote the first few terms up here, where I inserted in this expansion all the junk that is given here, in particular the Hamiltonian. Okay, so now let us go back to this simple identity that we have here and see that it is correct. Well, this is rather easy. Everything I do is easy. All the difficult things is homework and exam. No, I'm kidding. But let us see that this is gives you, this guy gives you back here. You can nearly see this maybe. So this is just a lesson how to operate with functions of operators. So I want to look at exponential minus I h t over h bar. This is acting on phi n. This is equal, let us write it like this. One, I'll just write the first few terms, and at home you can convince yourself with the others. I h t over h bar plus minus I h squared t squared h squared and 2 factorial, and then here you'll have other terms acting on phi. And you see what happens here. When 1 acts on this phi n, what do I get? I get 1. When h acts on this guy, what do I get? I get minus I e n t over h bar. The reason is, by definition, h acting on phi n gives you en. Now what happens when you have h squared? Well, h squared operating on phi n gives you en. And then you operate again with h, so you get en squared. And what will happen if you have h to the power 22? Then you'll have en to the power 22. So you can immediately understand, more or less, that here you have this series blah, blah, blah. And because phi n is not changing when h is operating on it, because it's by definition the Eigen state, I get this guy, and now I get a usual Taylor expansion. But now not of a Hamiltonian, but of simply some number. Yeah, you see this is a number, some energy state, and all these numbers. So this guy, I sum the infinite series, I sum it up quickly, and this is simply exponent to the minus I en t over h bar. Operating on phi n. And this is exactly what I wrote to you up here. This is what I told you I'll easily prove, and I actually did it.
But we can only use Taylor expansion when en is higher
I can do whatever I want. No, seriously. Okay, so you are right, but you are also wrong together. In a practical sense, for example, if I want to do an approximation, usually what I do is I cut down the expansion after maybe 1 term, 2 term, if I'm not lazy, maybe 3, I cut it. So it will be an approximation. But what I do here is I don't do any approximation because I sum the infinite series. I did not neglect the term that comes here at 5,000. It's all in here. So I summed an infinite series. And because of that, I didn't do any approximation. I didn't do anything which is wrong, or even if you want, this is exactly the definition of this operation because you need to have the full series. Later on you will see that sometimes you approximate by cutting this off. For example, in computer programs, that's what you do. You cut it off after the expansion and you make t small. I'll soon talk about it. Does this answer your question more or less? Okay, so yes?
This operator is called propagator because it gives us...
Soon you'll see why.
Time.
Yeah, more or less. Of what? Of the initial condition. If you will operate on the initial condition, that will give you the solution. Soon we will see that. That is an easy thing. So as was mentioned here, if we go back, I already wrote it down. So now, okay, now it is easy to see, as the guy in the front row said, that the wave function psi of t is equal to exponential minus I h t over h bar psi at time 0. So what do you have here? Here you have the state function, the wave function at some time t. It is given by this operator that we just discussed now, exponential of this Hamiltonian, and you need to operate on the initial condition, and that is the formal solution of the Schrodinger equation. Soon we'll see why. It's pretty obvious, I think. But essentially what does this thing tell you? Let's say, as a theoretician at least, you can think about quantum mechanics in many ways. One way will be, the main issue is finding this psi. But psi depends on the initial condition. System 1 has one initial condition. System 2 has a different initial condition. By presenting it like this, you see that the key general feature for one given Hamiltonian at least is to find this operator. This can be a difficult task. Once you find it, then you can operate on all kinds of initial conditions and see what happens for system 1, system 2, depending on initial condition. But essentially, this guy is what is important in quantum mechanics if you want to propagate in time. And you see it's a propagation because you start at time 0 and you plot here. So this guy is called the propagator. Something that progresses from initial state to some time t. And that is simply this exponential minus I ht over h bar. Maybe some of you don't see it or cannot see it right away, but let me just, so you know, when you go over your notebooks in the middle of the night, you will see why this is correct. So, I mean, what do we know? I mean, let us look at this. Let us assume that this is correct. Then what do I have here? I have exponential minus I h t over h bar. Then I have here the initial condition, the state that I started with. But what is the state that I started with? I can expand this state into the eigenbasis of the Hamiltonian into these phi n's that we had a few minutes ago. You are not too old, so I guess you remember. So I have a sum over n. This is a sum over this expansion. So, and I move the sum outside here. This is easy to see why I can do that. Then I have this propagator, Cn phi n. So again, Cn phi n, sum over n is the initial condition. But we know what is this guy doing. As I mentioned, I just proved it up here. This guy is equal Cn exponential, because h, this is a number, so h acting on this guy, it is simply minus I ENT over h bar Cn phi n. But this we know is the solution of the Schrodinger equation. This is what you had before in the beginning of the year in the classroom. So essentially, I'm not really telling you something really new. I'm just making a more formal or more professional way just to say here, this is the propagator, this is, so you know this dictionary, because many people will talk in lectures, the propagator is, now you know what it is. Okay, we can also, so this is proof number one, or proof one, I mean proof, maybe it's a too strong word. Now that you are now becoming used to functions of operators, you can of course immediately see this from the Schrodinger equation. So another way to see this is proof 2 or method 2. So let us assume that psi of t is exponential, the propagator, minus I h t over h bar, psi 0. First of all, immediately you see that at time t equals 0, it satisfies the initial condition, because at time t equals 0, this is 1. Okay, so the initial condition is good. Now, what do I need to prove this? I need to just take psi dot of t, and then let us see if this satisfies the Schrodinger equation. Now, how do I take the time derivative of this operator? Well, I expand it h1 plus h2, blah, 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 blah. And you know, each time I'll get a derivative with respect to t. And if you do this exercise, please do it. You can immediately understand that taking the derivative of this operator is very similar to taking the derivative of the exponential function. What will I'll get outside is minus I over h bar. E to the minus I h t over h bar psi 0. So you are used to taking derivatives of functions, and please convince yourself that by expanding it and taking derivative term by term with respect to t, that this is what you get. But this guy, what is this guy? This by definition is psi of t, because this is the propagator times psi 0. So what did I get here? I got here nothing but the Schrodinger equation. Of course, now you need to go backwards. I mean, this is just a proof that this is the formal solution of the Schrodinger equation. It's very easy to prove it once you get used to working with propagators and taking their derivatives, etc. So given that this function is so important, it is sometimes symbolized by a special letter. So we sometimes write or we define U. Anyone knows why this is called the U? It's not because all the other letters are already captured, but maybe that's a good reason. Soon you'll see why it's called U, not P This is the definition of this object. So this is the propagator. And now we want to show a property of this propagator. A property of the propagator is the following. So, but before that, I will just define what is the inverse of an operator. An operator A has an inverse A minus 1. We always assume that it exists. Essentially, this is true for our operators, such that A times A minus 1 equal 1. Of course, also the opposite is true. A minus 1 times A is also equal 1, because I can now multiply it from the left by A minus 1, and then by A. So you can switch this order, and it's given by 1. So a property of U of t, so this is just a definition. Not many, but there are every operator you want to think, let's say a matrix, think about a matrix 5 by 5, it's a Hermitian matrix corresponding to some physical observable. It has an inverse, and okay, this is the inverse. Now, a special property of the U is that U minus 1, well, it's nearly trivial, but okay, we will prove it because I like to prove trivial things. It's exponential I h t h bar. So essentially, you take the minus and you put here the plus. And this means that U minus 1 times U is equal 1. Now, if h would be a number, this would be trivial, because, so if the Hamiltonian is a 1 by 1 matrix, this is actually trivial. It's also trivial when h is not a number, but it's slightly less trivial, so let us show it just for the fun. That's what I mean by that. Later we would see, okay, so what if this happens? This is just a step. Well, how do you prove this? Essentially, you write 1 plus I h t. Again, this is some matrix. Let's write h bar is equal 1 for the sake of my sanity, minus h squared t squared over 2 factorial, blah, blah, blah. All this guy is u to the minus 1. And then I need to multiply it by u. Here I have I h t, this minus here because this is this minus. This minus is because I had I squared, right? And here I have minus I, no I. I have exactly the same, like here. So here plus, here minus, but here the same thing. H squared t squared over 2 factorial, and then I have further terms. So I need to multiply these objects one by one. So I have, first of all, a 1 times 1. So this guy is the easiest one. My claim is only these guys survive. So this is equal 1, you all see, because 1 times 1. What happens to the terms that are linear in ht? So this guy is linear in ht, and this guy is linear in ht. Okay, fine. So I multiply this guy by 1, I get a minus, and I multiply this guy by a plus 1, I get a plus. So here I have I ht minus I ht, and this guy is, of course, 0. What will happen to the next order terms? Well, I have here an h squared t squared. So again, now I look at the higher order terms. So I look at this guy and this guy when they are multiplied by 1, and I have one more high order term, which is this guy times this guy. So here I have minus h squared t squared over 2, and I have 2 of these guys. So this is this term, and then I have h times h, t times t, I times I. And you see I times I is minus 1, but here I have a plus and a minus, so it's a plus. So here I have h squared t squared. So this guy is 0. And then this continues, of course. So I prove that u to the minus 1, u is equal 1. All this exercise just shows again and again that when you want to prove something about some operator, you use the definition, the function of the operator, use the definition, you expand it, and then you can prove things. It's not exactly like numbers, but it's very similar, at least at these examples. Okay, now we're going to prove something else, and then you'll know why we called u in this name. An important property of the operator, the propagator, is the following. U minus 1 is the self-adjoint of u. This is the self-adjoint. It's a cross. Soon it's Christmas, so I'm allowed, even though in Ilan it's maybe not allowed. So this is something, a specific property of this operator, and in general, any operator who satisfies this strange-looking identity is called, do you know how it's called?
Unitary.
Yes, this is called a unitary operator. What I mean is that u in our example is unitary, but any operator a minus equals a, the adjoint. So adjoint, just to remind you, for example, if it's a matrix, you take the complex conjugate and you switch from above the diagonal to below. We know what this guy, or at least we were discussing it in the last 2 lessons, so I hope you remember. So we will soon see that this unitary, this fact that it is unitary, has some meaning in our evolution. And because it's unitary, that's why people use the letter u for this propagator, because it's a unitary operator. So to prove this, we have to remember what is u dagger. So u dagger is exponential. This is the definition, minus I h t, all this dagger, self-adjoint. So this I can write as, I'm writing this as the Taylor expansion. The Taylor expansion of the exponential is k from 0 to infinity minus I h t to the power k factorial. All this, I need to take the self-adjoint. So what do I do when I take a self-adjoint? If you remember, on t, on k factorial, it doesn't operate, the self-adjoint operation. It operates on h. What happens to h when you take the self-adjoint?
Self-adjoint of h.
It's h. Why? Because it is Hermitian. So now we are going to use the fact that h dagger is equal h. It is Hermitian. Of course, the same holds h to the power 22 dagger is also h to the power 22. So when I take the dagger here of h to the power k, I get k, and only thing what will change? The I will change to minus I. So this guy is simply equal to the sum over k from 0 to infinity, I h t over Here h bar is 1, yes? K factorial, k. But what is this guy? This is, of course, exponential of IHT. If you want to have the h bar, you can add it. Sometimes it's 1, sometimes it's not. But what is this guy? This guy is u to the minus 1. Just remember, u to the minus 1 was with the plus. U was the same, but with a minus. Now we saw that this is equal to u dagger. So u minus is equal to u dagger. Who cares? Well, soon you'll see why you care a little bit about this. So, essentially, you can view quantum mechanics as a transformation of a vector, because u of t is equal u, which is a function of t, times the initial condition. So you have some operator, you operate on it, and you move it to t. So if you look at these psi's as some vectors, let's say a line of a matrix, or of a unit vector matrix, I mean, this is just a transformation from one to the other. That is quantum mechanics. And you have here a unitary operator if the Hamiltonian is Hermitian, and it is always Hermitian. So a property of unitary transformations, it's more general than this guy, but let A be a unitary operator you have A phi equal some other psi. Not this is a math. I mean, it doesn't have to be that one. Then phi is equal to psi. This means the following, that if you have a transformation which is unitary, it conserves the norm of the vector. What does this mean in quantum mechanics more physically? Because u of t is unitary, we say something that you know, and that is, if initially the state function was normalized, and it is normalized from physical point of view, then also psi of t is not normalized. This means that the fact that the propagator is unitary, which is related to the fact that the Hamiltonian is Hermitian, conserves the probability, meaning that the norm of the wave function is always a constant, always equal 1. From physics point of view, you know why, because this norm of the wave function is just simply what is the probability of finding the particle in some state. So this is the probabilistic interpretation, and that's why you must have, as a propagator, some unitary transformation. Let us show this, why this is the case with our specific example. So let us show this Not in general, I don't want to do the math. I want to show it for the wave vector itself. We know, proof of a physicist. We know that psi of t is u. That's the propagator, which is a function of t. I'll not write that, psi 0. So again, this is this exponential function to the minus iht. Now you see why I prefer to have one symbol word instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 symbols. So u, that's all these guys. It's the propagator. Good. So now, because you are already experts in Dirac notation, and this is just to tell you that if you are not experts, you should go and read again and again. I already taught this, so if you don't know this, tough luck, go and read. Now we're using the beauty of Dirac's notation. Look how simple it is without integration by parts. I just look at what is the conjugate of this guy, just switching these guys around. So by definition, this is psi 0. And here I have to take the adjoint of u, like that. Now, this guy, okay, because H is Hermitian, u dagger is equal u to the minus 1, right? That's the property that I showed you in the previous simple proof that we gave you. That means that psi is simply equal, this is psi at time t, yeah? This ket, this is equal to psi 0 u to the minus 1. That was just a preparation. Now what do I want to prove? I want to find what is psi. Again, this is at time t. Let us add this time thing at time t. What is this equal? Well, I just have to copy this guy here. This is psi 0, u minus 1. What is psi t? This ket, u, psi 0. So this guy is simply psi t. And all this guy is psi t. Right? But what is u minus 1 times u? It's very simple. It's 1. So I get here that this guy is psi 0, because u minus 1u is equal 1. So and this is because of the unitary property. So what do you see here? The norm of the wave function, the norm of the wave function at time t, any time t, t can be anything, is equal to the initial norm, which if I start with 1 means that normalization is conserved. So this is conservational normalization. What is new here? We already showed you this at the beginning of the course. But now I showed you a little bit more general, and I introduced these words. Unitary evolution, that is very important, and general solution, and I did not do any integration by parts, so it's not necessarily in X domain, this wave function. It can be in any representation of quantum mechanics that you wish. This is why I call it still part of the formalism. It's not totally new, what I'm teaching you here, but this is the language of theoreticians in quantum mechanics. This is what you really need to know if you want to continue your studies to higher degrees. People will use the words propagators, unitary transformation, and you need to know this dictionary to make some advance. Okay, so let us have now a break for a change, so you won't be too tired unless you have questions. Let's have a 10 minutes break, and after the break, we will use this operator to understand better, or just to discuss briefly, the Heisenberg representation of quantum mechanics. I had a remark for this guy's question. So, for example, no, not yours. What's your name?
Me? Yao.
That's too difficult. Yomon? Yao Peng.
Yeah.
Okay. Yeah. Okay. So, for example, if you want to be practical, because this was a lot of formalism, you have psi of t. We proved rigorously that this is minus I h t over h bar psi 0, right? So, for example, now, if this h is not a diagonal Hamiltonian or it's something complicated, you might not be able to find this in diagonal form and then multiply the initial condition. It can be very complicated. I didn't solve here the Schrodinger equation in reality because this is a monster in principle. It's an exponential of some matrix which can be infinity on infinity. But I can do some approximation. Maybe this is what you meant, for example, on a computer program, which is 1 minus I h t over h bar psi 0. And that is if t goes to 0. It's an approximation of how you evolve on a computer some initial condition. So what you do here, what you need to think here about an iterative scheme. That is, I have the initial condition. I will use this approximation of the exponential because t is small, and then I'll get psi t at some small time t. Then what will I do? I will put this t and then propagate it again. So I'll have psi 0. This will go to 1 minus I h. That will be one step in your program. People like programs today. So this will be an approximation at time t delta t. From here I'll have this thing on my computer, and now I'll propagate it again. This is what people do on computer programs, but this is not the best thing to do. Why? So this is simply the wave function. And then you propagate it with some small delta t, one step after the other, and then you get a numerical solution of the Schrodinger equation. Yeah, I think you know this type of small delta t. This is what is done. So in this case, what we are doing here is we are approximating the Hamiltonian with the first order correction. You can do another thing. You can approximate it with the second order. If you don't like only one, you can do it a little bit better. 1 minus I h t plus minus h squared t, and then you can make a correction in your code and slowly propagate this. These are simple ways of discretizing the Schrodinger equation and propagating it on a computer. Of course, you gain some error because each step is an approximation. This is an approximation. This is an approximation. You know what is one bad thing about this guy? Time? Well, computers are always time, yeah, because you need very small delta t's, and then, of course, computers are not useful in the sense, if the Hamiltonian is complicated enough, you cannot really do too much, but, you know, let's assume that the problem is too difficult for us, but not tremendously difficult, so you can propagate. One problem here is that this guy, you should ask yourself, here you learn something, is this a unitary transformation? So you see, what am I doing here in this program? I'm evolving with this guy instead of this guy because this is an approximation. Now, is this guy unitary? or not? The answer is it's not exactly unitary, so after some time your wave function will not be normalized. Of course, as delta t goes to 0, it's better and better. But so you can replace this by all kinds of schemes where I approximate this by something unitary. So you will see, if you're interested in this, I can give you something to read. If you want to approximate numerically the Schrodinger equation on a computer, you better choose your propagation on this delta t, which is an approximation, but at least choose it as a unitary transformation in such a way that at least the wave function modulo square will be conserved. This is something you didn't know, I believe, before you came into this class. So you learned something new. So these type of considerations are super important. You want this, you want an approximation of this guy that is unitary, that still maintains at least the norm. Of course, this doesn't mean that the energy will be, the average energy will be conserved and other things. So building a computer program, for example, which is an approximation always, involves details that you must understand the generic properties of this this propagator. Okay, I just explained a little bit beyond the classroom, but just to tell you that numerical simulations are not totally trivial. Okay, let us see some general properties and conservation rules. In quantum mechanics. So, you know, for example, that in classical mechanics, if the Hamiltonian is time independent, then the energy is conserved. You know that if the system is spatially translation invariant, you know that momentum is conserved. So we would like to see under what condition is a physical quantity conserved also in quantum mechanics. When I say a physical quantity in quantum mechanics is conserved, what exactly do I mean? I will look now on the averages, quantum averages of physical quantities. But actually what I mean is that the properties of the operators associated with these observables under certain conditions, they will be conserved. What do I mean by that? What we are going to show, I will just tell you the bottom line and then we'll prove this. Let's say you have an operator A. Let's say it commutes with H. Then the average of A is conserved. So the condition for conservation, what do I mean by conservation? That the average of A is time independent, that it is a constant of motion, like energy is in classical mechanics. If there's no time dependent forces, it will be a constant of motion. So conservation here means we want to find the quantities which are constants of motion in quantum mechanics, and we will show that this is based on the question whether or not the operator is commuting or not commuting with the Hamiltonian. Okay, so to see this, let us see this. We will compute. We will look at the time change. Some general expectation value. A is some operator. It can be the position, it can be the momentum, it can be the energy, angular momentum, spin, whatever. We want to look at how these things change. Well, for that, let us again, in the millionth time, write down the Schrodinger equation. And to prepare, we want to write also, now we are experts on the Dirac notation, we're going to write this as a conjugate. So I know that I can write this like this. So I'm taking the adjoint, and I'm using the fact that H dagger, which I should have here a dagger, is H, because H is Hermitian. So I'm using the fact that H is Hermitian. This is equal to psi dot minus I H bar. Like this. So this is just one way. This is the usual Schrodinger equation, and this is the adjoint of that Schrodinger equation, using the fact that H is Hamilton is Hermitian. Okay, so now what is the change in time of some expectation value A? Well, what is the expectation value? It is given by psi A psi, where in principle I need to take these integrals or whatever, multiply these vectors, etc., and do this. Let us assume that the operator A is time independent. I can define an operator, for example, operator x times some function of t. That's also an operator, but here I'm going to say this operator A intrinsically is itself time independent, like most of the operators we saw up to today. There are, of course, operators that depend on time. For example, if I apply a time-dependent force, or I have a time-dependent Hamiltonian, which I have any time that for example, I have an atom here and you come with some radiation that changes in time, then my Hamiltonian will depend on time. We are not so much discussing time-dependent Hamiltonians, but in principle, of course, this happens all the time in real life and in many laboratories. Essentially, I'm assuming that both H and A are time independent in this thing. I'll briefly explain what will happen when A also itself explicitly depends on time. Simply, what will happen is the following. I take the derivative, so this dot is the time derivative A psi plus psi A psi dot. What will happen if I have if A itself will depend on time? Well, I'll have another term. So here I have psi dA dt psi. This guy is equal to 0. Later I'll just give you the result when I have a certain, because I have here two terms. Two terms is already too much. Let us stop here. So now I have this guy here. I know what this guy is, because you see I have here psi dot. I have to take this guy and I have to divide it, and then I'll get here the following, minus 1 over I h bar. So you see, I take this, I divide here by minus I h bar to get psi dot, and then I have here psi. This is good news, because now there's no dot here anymore. I got rid of this dot, and now I have this h. Again, because it's Hermitian, the adjoint here turned into h, so it's h. Now I'm continuing the writing. Now I have here the A. Now I have the psi. Here I have psi. Okay, let us leave it because it's not a derivative in time. A, okay, it is what it is. Now I have psi dot. What is psi dot? Okay, here I need to divide by 1 over IH. Then I'll get essentially h with this thing, but with a minus sign. Okay, so here I'll have h psi, and I need to divide here by 1 over IH bar, by this guy. Here there's no minus. Right. Now look at this slowly. What do you see? Good. No. Most of the question that I ask, the answer is 0 or 1, but it's only when the answer is a number. When the answer is not a number, then you cannot use that rule. What do I see? What do you see here? What do you see here?
If they are commutative, it's 0.
Yeah, you see the commutation relation. So I see here the following. I see here 1. I can take this upstairs, I over h bar psi h a psi. So, to summarize this, let us assume also that you have a time dependent, and in principle, let us add it, it's just adding that term. In general, In general, what do you have? You have d over dt of A is equal I over h bar psi h a commutation relation. Remember that this bracket is the commutation relation of h and a, psi plus psi dA dt psi. This is a general, this is the general dependence on time of the average expectation value. In particular, if A is time independent, and the commutation relation H and A is equal to 0, then d over dt A is 0, and this is what I meant. A is a conserved average value of A. So A is simply conserved, which means A is time independent. Because its derivative with respect to time is 0, it means that this is a constant of motion. And again, what is the new thing that you learned? In quantum mechanics, to find if some quantity is not changing in time, you need to know, essentially, its commutation relation. It's another example out of many of the importance of commutation relations. Let's give two simple examples. Assume A is P and H is P squared over 2m. Of course, this is the simplest Hamiltonian where there is no force field acting on the particle. The particle has a mass m, but you are looking at just kinetic energy, and P is the momentum. Of course, trivially, P and H is equal to 0, because P, the operator P of the momentum operator, commutes with P squared. It commutes with itself. So this is trivial. So it follows that P average is a constant. This is, of course, not surprising, because all it says that the average momentum, if there's no forces, is a constant of motion. This is also what you know from classical mechanics without using a commutation relation. So this is kind of well known and very well expected. Another example, let us take A equal x, the position, and let us have a slightly more complicated Hamiltonian, which is P squared over 2m plus some potential v of x, some function of x. It doesn't matter what it is. Now, to find out what we want to find is what is the time dependence or the derivative of time of x average. What is it? What is this equal to? So what does this equation tell you here? You need to, here x is a time independent. So this guy is obviously 0 because x itself does not depend on time. So this term is gone. So to find the change in time of the average position of the particle in this in this potential. So I have some potential. This is v of x. This is x. And I want to find its average position. This time is 0, and I need to calculate this commutation relation. So I need to find x h and h with x. What is this guy? And then I'll know the answer, or at least I'll know part of the answer in principle. I need to find this guy here. Now this Hamiltonian contains two parts, kinetic energy and potential energy. The potential energy depends on position. So of course v of x will commute with x. We can throw that part away, and this commutation relation is simply p squared over 2m x. So essentially, to solve this problem, all I need to do is I need to find what is p squared x. What is this? If I know this, I solve the problem. And this is something you had, I guess, in your homework or maybe even in class. Let us do it again. So p squared commutation relation with x is p squared x minus xp squared. The way I do it is I write it as px minus xp. This will give me p squared over x, but it will give me another term. And here I want to write this as p outside here to get this p squared. And here I'll have xp. Here we have px. I mean, everyone has his own tricks. So you just see, this will be with a plus. This will be with a minus. Here you see xp squared is this guy with this minus, and here you see pp is this guy, and here in the middle you have minus pxp, and here you have minus minus, so this is pxp. And why do I write it like this? Because, okay, this is the commutation relation, so here I have px. So this is p times p commutation relation with x. And this is guy is minus, this is xp minus px, so this is xp p. But this guy is minus ih bar, and this guy is plus ih bar. So all of this together is simply minus 2ih bar p, the operator p. So it follows that hx is simply, now I need to take this and just divide it by 2m. So it's minus I h p over m. So if I plug this now in here, identifying this a with p, and I'm using our Hamiltonian, then I found the following: dx average dt is equal to I over h bar times minus I h bar over m p average. The average is because you see here I still have the average psi on both sides of this commutation relation. So here this cancels, I times minus I is 1, and here I get p over m. So this is the final answer, that the derivative with respect to time is simply the average momentum over the mass. This is not new. This is the definition of what is a velocity. And this is also what we called at the beginning of the semester. This is Ehrenfest's law. At the average of the expectation values of x follows what we expect from classical mechanics, which is the velocity equal average momentum over m. This is, of course, not new. What is new is this guy. This guy is new. Now we are, again, reformulating, you want in some way the Ehrenfest laws, but in much more general way, because now any a that I want, I can plug in here, do the commutation relation, and get the average time dependence, while Ehrenfest was limited to very specific observable. That is the momentum, and average position. But now we can do it. I can do many, many time dependencies like this. So this guy is the general thing, and Ehrenfest is a special case.
I have a question. In classical mechanics, if the Poisson brackets Hamiltonian and maybe F equal to 0, the F is time independent. I think it's very similar to this commute.
Right. So you're absolutely correct, but so there is a relation we are not so much discussing between the commutation relation and the Poisson brackets, but there is one big difference, and that is, of course, that here we have this h bar. So there is a relation, but in classical mechanics, the bottom line is there's no exactly h bar, but this is very similar. If you go look at, for example, I think in Cohen-Tanuji at the end, he discusses this more. So yes, you're right. Okay, I'm not expanding on this too much. But because eventually you need this h bar. So, but you can think about this commutation relation as a generalization of the Poisson bracket, not exactly the same, but related. Okay, because the Poisson brackets are related to conservation laws, and that's what you mean, etc. Absolutely correct. Okay, so now we want to go, and as I already promised you, I'm going to discuss now Heisenberg relation and change a little bit, for a while at least, your point of view on quantum mechanics. Then you can forget it and thinking like in Schrödinger. So the Heisenberg picture. Heisenberg. The meaning of picture is the point of view on quantum mechanics. What is the idea? I will start with what you know, and you know the Schrödinger interpretation. So let us look at the Schrödinger interpretation. For example, an average. We have an average, let's say A, some average. We just dealt with this. What is this thing? It is psi of t, the wave function that depends on time, A, psi of t. Now, let us think a little bit. What is this psi of t? I can write it like this. Psi 0, because we know the evolution operator. What will I have here? I'll have here u dagger. U dagger, remember, is equal to u minus 1. This is simply the fact that psi of t, as I already said in previous lesson, is e to the minus I h bar h t over h psi 0. So I just take the inverse. This is u, and then I operate. It's u dagger, but u dagger, what is this guy also? U minus 1. So we will discuss it. All this is valid. A. Here, what do I have? U psi 0. Now, when I look at this like this a little bit, where is the time dependence? Well, it's in these operators. These operators, these guys, they depend on time. So the philosophy of Mr. Heisenberg is this guy is what is changing in time. These states are not changing at all. So his idea was we will look at operators that they themselves are changing in time. So let us add to this here the word S. What is this S? Schrödinger. That is some operator in our language, our vocabulary that we use up to today. And after this lesson, we'll go back to that. So I will not use A of S to the rest of the course. So most of the time, A will be A of S, S Schrödinger. So for example, this is the Hamiltonian. This is the momentum operator, or everything that you know, position, whatever you like. And now let us define some operator, which I call AH. What is H? It's not H bar, HH Heisenberg. So this is the title of the man, and this is also the title of the guy. And this is guy, we're going to say that this guy is ASU. This is the relation between the two worlds, 2 points of view. Of course, when Heisenberg will object to what I'm saying, but I don't really care because okay, I said I don't like him so much, but also because most people use this guy. But of course, you can invert this because you can put this guy here and then you can multiply here by u minus 1, and then there is a transformation from Schrödinger to from Heisenberg to Schrödinger. But simply because you know what is Schrödinger, so okay, so this is a new definition of something. This is just the definition. So what if you just need to remember the general point of view, is that we have two pictures. So I'll simplify a little bit the discussion. Again, this is not major issue. Let us assume AS is time independent. This is all what you know, PS, H, X, L, orbital angular momentum. There are many, many more operators, of course. L we will learn in next lesson, so start reading about L. It's a very complicated operator. Well, I'm kidding. It's complicated before you study it. After you study it, you will understand it, but you need to read a lot about this operator L for the next lesson. So anyway, let us assume that these guys are not explicit. These guys are examples of operators which are not explicitly time dependent, just to simplify the picture. And then we have the Heisenberg picture. Oh my God. This is HI. Picture. Then we have the Schrodinger picture. And in these two worlds, which are totally equivalent, we have a wave function. We have an operators. And in Schrödinger picture, what is the wave function? It is time dependent in principle. It evolves in time. But what are the operators? They are fixed in time. These are matrices. They are operations. Minus I h d over dx momentum. It doesn't depend on time. So these are time independent. And in Heisenberg, essentially, what you saw from the equation that was just on the blackboard, what is the wave function? It's time independent. What is it actually? It's the initial wave function, whatever it is. This is time independent. This is time dependent. Again, why is it time dependent? Because the propagators depend on time in Schrödinger's language. So these are the propagators in Schrödinger language. Yeah, exactly what I had before. This depends on time. This depends on time. So AH depends on time. We can write it explicitly like this because of these time dependencies. Now, the operators depend on time, right? So as a physicist, what will you do if they depend on time? you want to be famous, you want to get a Nobel Prize, you think that the operators depend on time, you look for an equation of motion for these operators. That was what Heisenberg did. Not, by the way, I do it because I come from Schrödinger to Heisenberg, and that is what we're going to do. We want to, this is some function of time. It's very complicated. I'm going to write an equation for this. Of course, I can, this is already the formal solution. Formal because these guys are just monsters in general, but let us look what is the equation of motion for this operator AH. And that will be the basic equation, if you want, what replaces the Schrödinger equation in Heisenberg's picture. So we are looking for the equation of motion for this operator, which now depends on time. Again, Heisenberg did not do this. I don't know how he did it. He was very clever. Practically, he had to guess it, because this is exactly on the same level of saying this is the Schrödinger equation, this is the Heisenberg equation. So this is really magic, what was originally done by Heisenberg. Okay, so what is the equation of motion of AH? Well, we are kind of lucky. Again, let us look, for example, okay, let us remind ourselves, A, this is, of course, equal, again, psi of t, A Schrödinger, this is just a slight repeat. This is equal to psi 0, u to the minus 1, A Schrödinger, u psi 0. And this guy is what I called A Heisenberg, all this guy, right? So AH, or it comes from here also, of course. AH, so let us take the derivative of time of AH. That is the same as the derivative of time. This is the definition of ut. Remember, this guy is ut. I can choose to write a u minus 1, but I choose to write ut. It doesn't matter. As u. This is the transpose. It's the same as the u to the minus 1. It's all written here, right? So I need to take the derivative. So here, this Schrödinger equation, I assume that this operator, no time dependence. It's not difficult if this guy also depends on time, because then I'll have, you see what I have here? It's just the chain rule of derivatives. I need to take the derivative of this guy, the derivative of this guy, the derivative of this guy, multiply. Like you multiply, you take the derivatives of functions. Let us assume this guy does not depend on time. So here I have u dagger dot as u plus u dagger as u dot. What is this guy? U dagger dot. Well, u dagger. Let us look here. What happens when I take u dagger? I take IH. Let's write it here. U dagger dot is IH. You see here? EIHT. H bar is 1. Now I use the fact that this H, does it commute with this guy? I can replace the orders. I can put this guy here because this is a function of H. It's commuting. Exponential of IHT commutes with H, so I can put it here. Then this guy is equal to I exponential IHT times H. This is I U dagger. This is U dagger H. Okay. This is it. It is what it is. Remember, h bar for now is 1. Later, it's good for you put in the h bar to check all the correct units. So this guy derivative is I, that I, u dagger h as u. Okay, hallelujah. Here, when I take the derivative of u dot, what do I get? Let's look, u dot. I get minus IH, h the Hamiltonian. Okay, so u dot is, when h bar is equal 1, is minus IH u. Because all these guys, this exponential, when I take the derivative of the exponential, I get this IH, right? So let us write it down here. Then I have u t as, let us put the I here. Here I have minus h u. And this is as, because this is the Schrödinger guy. Now, what do I want? I have here as. I have here as, but what do I want? I want to write an equation, not for as. I want to write an equation for ah. Now, this as, here it's multiplied by u. You see, as, this is the definition, as times u. But what would I really like to have here? U minus 1. U minus 1. How can I put here u minus 1? You don't know.
Replace between the...
I can do the following simple trick. H, I can't just plug in here u.
By u and then
Exactly. I can plug it by u, then by u minus 1. Because this guy is 1. Then I have as u. And the same, okay, u minus 1 and u dagger are the same, right? Sorry for the mix-up. And then here I have I, u, t, as, and now I'll do the same trick, u, because again, okay, soon you will see u to the minus 1, because again, this is 1. Here I have minus h times u. So I just added the 1 in between, that's allowed, and this is a property of the unitary transformation. So last lesson I told you that u minus 1 and u minus 1 is u the dagger, so that's why I can identify this guy with u minus 1. So I get here the following. So I, what is u dagger h u? All this guy. What is u dagger h u? Remember, u dagger is u minus 1, so what is this guy? This is h of Heisenberg. It's a bit annoying that Heisenberg has the same as the Hamiltonian, but it is, because again, this is the transformation of the Hamiltonian, but if the Hamiltonian is time independent, it's not so bad, because h will commute with u, and then this is essentially the same as the Schrödinger Hamiltonian. But okay, let us write it as this transformation. For example, if h would depend on time, then this would be important. But in principle, no problem. If h would depend on time, by the way, this equation by itself would not be correct, if you think about it. So, but we are going to write it as h of Heisenberg following this transformation. And what is this guy? This is A Heisenberg. And here I have the minus I, and here I have, again, u dagger as u, that's A Heisenberg. And So these three guys go to this guy. And then I have u to the minus 1. U to the minus 1 is, of course, u dagger. Hu, well, that's H Heisenberg. Hallelujah. We found the equation of motion. And what is this guy? H, A, H. With the minus sign in the middle. Forget the I. This is, again, a commutation relation. So the basic equation, according to Heisenberg, is the following. Now, okay, now, I don't know if you like it, but I don't care. Now h bar is not equal 1. I put it back. And then I have I, h bar. Simply, I divide this equation by I. And then I have to switch this order when you do the commutation relation. Because when I divide by I, I'll get minus I. And I replace the I. D over dt. A of h. This is equal to A H H H. Now I'm putting something by hand. Let us assume that this A also depends on time. So I prove to you this part because this is the most important part from my point of view. The commutation relation gives you the time evolution of the operator itself. And you can add to it, if you have a time dependence, IH bar, dAh over dt. Please prove that if the operator itself depends on time, you will have an additional term. So this is an additional term. Again, this part I proved, this part I just tell you because it's very simple, because it's just the other term here that I'll take here, the time derivative. So this is the basic equation.
It's if AH or AS, it depends on time.
AH depends on time, because by definition...
AH by definition depends on time. Always.
So this should be AS. No, because, okay, here I have, it's a bit, you're right, thank you for this comment. Because here I have A, UT. Okay, so let us write it like this. What did I neglect? I have here UT, AS dot, U. This is what I mean by this. Okay? Yeah, thank you very much. It's an important question. So this is the definition, if you want, of dH over dt. So the meaning of H is the following. I take this operator and then I multiply it by the two sides. Okay, but again, most of our discussion, this term doesn't exist at all because the A itself, the operators themselves do not depend on time. So this is the basic equation of quantum mechanics. You can think about it, this is the equivalent of the Schrödinger equation, but it was derived by a guy called Heisenberg. He was an expert, unlike Schrödinger. His teacher, I guess, was very good in linear algebra. So he thought about these A's and these H's as some matrices. And they have this commutation relation. And he had no second derivative in space, like kinetic energy, all these things. He had this. But what I showed you now is that these two things are obviously the same. Why are they obviously the same? Exactly the same thing. They're the same thing because, as I showed you, when I calculate an expectation value, the average of A, it gives you the same result. So there's no difference between the predictions, at least on expectation values. Now, in quantum mechanics, you cannot measure, even according to Schrödinger, you cannot measure psi. So you cannot also measure these operators. So the fact that in one picture the wave functions depend on time and the operators don't, and the other picture the opposite, it doesn't matter, it's not important from the point of view of measurement. Because anyways, you don't measure directly the operators, you don't measure directly the psi's. What you measure is you can measure expectation values by doing many experiments and things like that. But essentially, there is no difference between these two representations. So if you ask historians of science who invented quantum mechanics, the answer is both Schrödinger and Heisenberg. Very different pictures, but essentially the same thing. And because, as I mentioned previously, Schrödinger is more popular, we will mainly use his language. But it's just a matter of language and convenience. There are still people working on this type of definition. From now till the end of the class, to the end of the semester, we will study problems in 3 dimensions. Our goal is to understand real systems, and real systems are in 3 dimensions. So the first thing we will study is a particular example of a particle in a box. So you should start thinking not in 1 dimension, you should start thinking in 3 dimensions. And for that, there are many, I would say, technical extensions of quantum mechanics that we studied up to today. When you go to 3 dimensions, things are much more interesting and also slightly more complicated from a mathematical point of view. So we will start it, so quantum mechanics in 3 dimensions. And we will start, just as an appetizer, with a particle in the box. Because this is a super simple problem, I start with an example, and then you will see what is the difference when a particle in a 1-dimensional box. So, the following, so this will be a particle in a box. So what are the questions? These are, of course, general questions. These are, what are the energy levels of the system? How many quantum numbers do we have? Describe the wave functions. Essentially, at this moment, I'm only considering the time-independent Schrodinger equation. I want to know the energy level, so I'm thinking about some spectroscopy experiment that measures the energy levels. I don't care about time, because once you go to 3 dimensions, it will be complicated enough to calculate the energy levels, and our goal maybe in 2 or 3 lessons will be to calculate the energy levels of the hydrogen atom. That's more or less the end of this course. So that's where we are going. So how many quantum numbers do describe the wave functions? Another element is what is the degeneracy. So up till now, we maybe mentioned a little bit the degeneracy. The degeneracy means that a certain Eigen energy, a certain energy of the system, maybe can be associated with more than 1 set of quantum numbers. We mentioned this, but you will soon, very soon, see that this is in 3 dimensions. It's much more pronounced than in 1 dimension. So when you go into problems in 3 dimensions, you see a lot of degeneracy, and also you will see that degeneracy is related to what? When do you have more degenerate states and when are they less? What is controlling the degeneracy? Well, that is the definition of the degeneracy, but it will be something else. It will be the symmetry of the Hamiltonian. So when the Hamiltonian is very simple and symmetric in some sense, you will see the degeneracy is high. And when you remove the symmetry, we break the symmetry, we make the system more less symmetric. I'll soon explain what it means. The degeneracy is removed. This we will see already for the particle in the box. These are the type of questions, and these are not only limited to this particular problem. So what is the problem exactly that we are treating? So we are going to treat a box. A box means that we are working in a very particular set of coordinate systems, and that is, of course, the Cartesian coordinate systems. In general, when we work in 3 dimensions, we can work with many different types of systems. Cartesian, the spherical, the cylindrical are most famous, and these guys, you will have to know all of them to solve problems in quantum mechanics, which actually means the following. Now you start thinking, how will I describe, let's say, momentum in spherical coordinates? Up to now, it was always, we used always Cartesian coordinates, because what was the momentum? Minus IH d over dx. And then what is the momentum in the z direction? Minus IH d over dz. That is what I mean by that I'm using up till now always Cartesian coordinates, but you know, if you have some potential, for example, in the hydrogen atom, what is the symmetry of the hydrogen atom? It's spherical, because the Coulomb potential cares only on the distance of the electron from the proton in there, so you have a spherical symmetry. So obviously, if you have a spherical problem, you want to work with spherical coordinates. So you will need to, how do you, for example, define the kinetic energy in different sets of coordinate systems? You need to know this. I mentioned this now because you need to already start reading this for next lesson. Today we will still use the Cartesian coordinate. Why? Because I define a particle in a box. What is a particle in a box? Well, I have a right-hand coordinate system, x, y, z. I want to put it like this. Yeah. X, y, z. And then I draw here a box. Oh, my drawings are so bad, you have no idea. Not so bad. Okay, so this is a box. And what is the potential? The potential outside this box is infinity. Every point outside the box is infinity. Inside the box, the potential is 0. So this is like this room, right? Here, this size is a bit less than that size and this size. And unfortunately for you, you are all trapped inside. You cannot leave this room, so that's why the potential is taken to be infinity outside here. Now this box has 3 scales of length, and in the x direction, this size is A. In the y direction, this is B. And in the z direction, the size is C. So the volume of the box is A times, I don't like x, A times B times C. This is the volume of this box. This is volume. No, that's why I have this. It's not the potential. The potential is 0 inside, infinity otherwise. And like the particle in this is like, we solved a similar problem in 1 dimension. That was the particle in 1 dimension. Remember, we solved this type of problem in 1 dimension. So this was 0, this was A, and here we had infinity. These 2 problems are, of course, very much related to one another. This problem is in 1 dimension, but this problem is the same, but in 3 dimensions. It's, of Of course, you can do it also in 2 dimensions if you want. And so we will solve this time-independent Schrödinger equation. So I need to write, what do I need to write to find the stationary solutions? Stationary solutions, I need to write the Schrödinger equation, and the Schrödinger equation is H phi E phi. Let us leave out what are the quantum numbers for now. Let us say we don't know them, but soon we'll get them. What is H? What is H here? Well, you have this potential, but we don't care, about the potential, because the wave function out here, it has to be 0. And the boundary conditions are also more or less obvious for you, I hope. So what do we have here inside the box? We have here H is only the kinetic energy. And the kinetic energy inside the box is px squared plus py squared plus pz squared. And this is divided by 2m. So this is px squared, the operator, over 2m, plus py squared, over 2m, plus pz squared, over 2m. And this is the Hamiltonian. This is the kinetic energy in the Hamiltonian, of course. Okay, you have plus v x, y, z, which I defined. That is the Hamiltonian. So if you work in the box, x is between 0 and a, y is between 0 and b, z is between 0 and c. What is the Hamiltonian in this region? H is the following nice thing. It's h squared over 2m, the Laplacian squared. This guy is the Laplacian. Why do I say this? What is px? It's I h bar d over dx. Py, the same with d over dy. So when I square them, I get h squared and the minus from the IH, right? That's the minus IH squared. And then I have the second derivative in x, the second derivative here in y, the second derivative in z, and that is the Laplacian. If you don't remember what is the Laplacian, it is in this coordinate system, this nice object. And just to make you a little bit curious, so what will happen when we will work, let's say, in the hydrogen atom? You have a spherical symmetry. So then you will need to present this Laplacian, which is the kinetic energy, with spherical coordinates. But you are supposed to know already, I think you know, I'm sure you know, guys, that how to present the Laplacian in different coordinate systems. And if you don't, go to Cohen Tanuji or remind yourself for next lessons, because this is going to be important. Now, here I have this phi. Let us talk about this again. So this is our Hamiltonian. What is phi? Phi, let us go back, not to the Dirac notation. Let us start with the simple notation. It's a function of x, y, and z. Soon we will specify the quantum numbers. So this is obvious. It's a function of all space. So I have inside the box, I can make a very small box. Let us say I'm in a stationary state, and then I can take the absolute value of the wave function here times the size of the box. This will give you the probability of finding the particle in this tiny box up here, exactly like in one dimension, but in one dimension I had the wave function squared dx. Now what do I have? The wave function squared, a small element of volume is called dv. Not d potential, dv, d volume, which means dx, dy, dz. And that means the following. That what is the units of this guy? This is 1 over volume to the power half. In one dimension, the units of the wave function were 1 over length to the power half, because the square of it is the probability density. And here you have this guy. And what is the normalization? That is, let's say you have a state function, some function, this is only stationary, but I could also have here a time-dependent solution in principle. It's the same thing. Absolute value, dx, dy, dz. So all this is probability of finding the particle in a volume delta V, whose size is dx, dy, dz, around x, y, z. And what is the normalization? I need to integrate 3 times. Wow. Before we had 1 integral, now we have 3 integrals over x, y, and z. All this guy is equal 1. How do I write it in Dirac's notation? This is much easier. I don't need to write 3 integrals. I don't need to write anything. I write phi, and the meaning, of course, is depending on the context. If you work in 1 dimension, if you want to think about integrals, fine. In 1 dimension, this will be 1 integral. Here it will be 3 integrals. In principle, what are the, in general setting, this will be from minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. But in our problem, we are all understand this is from 0 to A, 0 to B, 0 to C, because the particle, that's the boundary condition, the particle cannot be found where the potential energy is infinity. That is impossible, because then the energy will be infinity, and then we will have no energy problems in the world, and that's impossible. Okay, so what are the boundary conditions? They are also pretty trivial, but they are the same like in 1 dimension essentially. In our problem, so the usual setting will be that these phi's will decay, and at infinity there will be 0, and their derivatives, all these nice things. So here we have phi. How will I write it? A or 0, y, z, this is equal 0. So if the position x is either A, which is here, or 0, which is back there, your wave function is 0. So on the boundary, of the box, phi is equal 0. Exactly like in 1 dimension. In 1 dimension we have 2 points, and here we have a surface. All around this box everything is 0, because we want the wave function to be continuous like in 1 dimension. So here it's 0, and then out here is also 0. How do we solve our Hamiltonian? Oh, I already deleted our Hamiltonian. But what was our Hamiltonian? Essentially, it was the Laplacian. What is the symmetry of the problem? It's obvious. Really the symmetry, what do I mean by that? Well, you have the Laplacian. The Laplacian I can choose right in many coordinate systems, but the boundary conditions obviously imply that this problem has a very natural symmetry, which is the Cartesian symmetry. And that's why, of course, I'm solving this problem in Cartesian symmetry. And because of the symmetry of the boundary conditions, if you think about it again a little bit, what is the solution, or what is the method of solution at least? I have h, let us write it again, minus h squared over 2m, d over dx squared, plus d over dy squared, plus d over dz squared. So I'm going to guess some phi of x, y, and z What is the solution? How will the solutions look like? It's easy to convince yourself that I'll have here a function which I call big X of X, a big function of Y, and another function of Z. This, as a physicist, I immediately understand this because you have the symmetry of the problem, and if you have a symmetry, then I can separate it into 3 problems, X, Y, and Z. This method is called the method of separation of variables, essentially. Where did we do it? We did it already. Where did we do it?
Schrödinger time-dependent.
Exactly. So we did it in Schrödinger time. When we had the time-dependent Schrödinger equation, we guessed a solution, which is a function of time times a function of x. And then we separated it. This is how we got from the time-dependent Schrödinger equation. We got a simple trivial equation for the time dependence, giving you this exponential, and the time-independent Schrödinger equation. Essentially, of course, here we have no time dependence, but we have here 3 coordinate systems. I can act on this guy. This has to be equal E, the other guy. Then I divide by all this junk. Then I get one function of x is the same as a function of y, etc. I'm not going to do this, but this separation of variables, ansatz, you know already. If you don't remember, then please go again after this. And then you will easily show that the wave function in each direction is very simple. Small m is the same as small m is the same as big M. I'm sorry. There's only one mass of the particle. And this is an energy. Soon I'll explain how this is related to the total energy associated with the solution of this part of the equation. And here I have h squared over 2m, second derivative y. So these 2 lines is the second derivative with respect to the variable in the parentheses. So this is the second derivative with respect to x. This is the second derivative with respect to y. Here I have ey, y. And of course I have the same equation for the function z. This is super simple because all what this says is that I can decompose the 3-dimensional problem into a multiplication of 3 one-dimensional problems. Because the boundary conditions are symmetric, I can separate it, and then I have these multiplications. The total energy is simply Ex plus Ey plus Ez. Again, if you don't see this, just plug it into the Schrödinger equation, and then you will see this guy. What will happen? You have this guy. It will operate over this guy. What will it give you? Ex. Then and it doesn't change these guys. Then you operate with this guy. You operate on this guy. This will give you Ey. Then you operate again this guy on this guy. You get Ez. So you see that you get Ex plus Ey plus Ez multiplied by the wave function, and that is exactly the definition of it. An eigenvalue problem, H acting on phi, gives you the energy, which is the sum of these energies, and you can see it. And if you don't, take your envelope and write it down, and you will immediately see that this is a solution. Namely, what I mean by solution, we are solving H phi equal E phi, as usual. Okay, so up to now everything is super simple, and everything we're going to talk about today is going to be super simple, because these problems you know how to solve, because we solved them already. See, quantum mechanics is a very easy subject. What did I actually do here? I took a 3-dimensional problem, I used the symmetry, and I reduced it to 1 dimension. Of course, this is what we always do in physics. When you have the Kepler problem of a motion of a particle around of the moon around the Earth, or the sun of the Earth around the sun, you try to find a coordinate system where you go from 3 dimension to 1 dimension. How do you do that? You exploit the symmetries. Here the symmetries are super simple. These are Cartesian. In Kepler's problem, you exploit the fact that the force field depends only on the distance between the particles. You use Cartesian systems. So essentially all what I'm doing here is obvious from physical point of view, exploiting a little bit the symmetry to make a 3-dimensional problem into 1 dimension. Because 1 dimension is super easy. For example, I can have the wave function in the x direction is nx. What is this guy? This is normalization. It's not so important because I don't need to normalize this guy because I can eventually normalize all of it together. But it's some constant if you wish. What is more important for you, the solution is sine nx pi a over h bar. What is nx? Is the quantum number. And nx is 1. It cannot be 0 here. Unlike the harmonic oscillator where you start from 0, here nx is 1 because 0 means no wave function. So you start from 1, 2, and you go to infinity. Why is this the solution? You know this, but just let me remind you, if you take the second derivative here, with respect to x, I get the sine, and then I get the cosine, and then I get again the sine, with the minus sign, and then I get here outside the sine equals the sine, and I get an expression for ex, which is, what is the time now? H squared nx.
4:36.
Quarter to 6?
No, 4:36.
Okay. ma squared. Here I wrote h, not h bar. So I have here an 8 and I don't have here pi's. Again, how do I do this? I take the derivative. Here you see I get pi squared, a squared. This is nonsense. Sorry. X, a. Of course. So when I take the derivative here, I get a, 1 over a, and then another time 1 over a. And then I get this expression. Remember that you get this quantum number squared. And here I have h over a squared. That is like units of momentum divided by m. This is perfect. You know everything about this, or hopefully you know. And okay, I see you're also tired. You didn't correct me. That's not so good. Okay, so what is the wave function? We can just write it down. Let us summarize. What is the wave functions? So this is the summary. I solved the problem in principle. First of all, we learned something new, or not so surprising. We have 3 quantum numbers, nx, ny, and z. All of them operate between 1 till infinity, 1 to infinity. Why? Because, okay, we have 3 problems, and each one of them gives you a quantum number. And because we're walking in 3 dimensions, then we have 3 numbers. Immediately you understand, if I walked in 5 dimensions, how many quantum numbers I'll have? I'll have 5. But our world is 3-dimensional, so we talk about 3. This guy is a function of x, y, of z. When I normalize everything, I get the following. I have a, size of the box, c. All this, here there is an 8. And this guy is to the power half. This is the units, this is the volume of the box, and you see that the units correctly are 1 over square root of the volume. This is 1 square root of the volume of the box to the power half. So when you square it, it's 1 over the volume. If you have a small volume, this gives you a probability density when you square things, of course. And the wave functions are simply sine nx times x over a. So again, at x equals 0, this is 0. That's the boundary condition. And x equal a, it's also 0 because these are integers. That's the quantization rule. So the boundary conditions are satisfied, and the derivative with respect to x gives you the correct number. Here you have sine pi ny, another quantum number y, over b sine pi nz times z over c. Good. We solved the problem in 3 dimensions. It satisfies the boundary condition. It gives you the correct energies. We are all happy and satisfied. What we see is number of dimensions, number of quantum numbers. So, for example, for the particle in the hydrogen atom, you will have 3 quantum numbers. For each Eigen energy, there will be 3 because it's a 3-dimensional system. It will be the same like here. What is the energy? Well, just have to take the sum of the energies, as I wrote before, like up here. And this is given by h squared over 8m nx squared, like here, over a squared, plus ny squared over b squared, plus nz squared over c squared. And this is the energy, and it has 3 indexes of quantum numbers. Now you need to start thinking how do you define operators in 3 dimensions. So it's rather simple. Many of the extensions are simple. The technical details, conceptual issues are simple, but maybe technical issues can be more complicated because it's 3 dimensions. So for example, what is the position operator? Well, I'll denote it by r. That's a position in space. And then that is, in this problem, it's obvious we will use Cartesian coordinates. I don't know if, I think this is well-known notation. These are unit vectors. I guess it's the same in China. Is it the same in Israel? Well, okay. X, Y, Z are unit vectors along the X, Y, and Z direction. So I think you know this. Sometimes they are called I, J, K. I like to call them X, Y, Z. So these are unit vectors along the direction. So this is an operator now, a simple operator of position. So I can ask, what is the R average? Now R is a vector. Up to now, X was the position of the particle. It was a point in 1-dimensional line. Now it's some average position in the box. And that will be very simple, X average times X plus Y average times Y times Z average times Z. So it's a vector. And what are these averages? In our case, it's super simple, right? Because it's like in 1 dimension, what are the averages if you have from 0 to A? The average, if you are in a stationary state, smack in the middle, right? So I don't need to do the integrals. It's super simple. And this is equal a over 2 x plus b over 2 y plus c over 2 z. Of course, provided that you are in a stationary eigenstate of the system. But in general, how will you calculate this? This is simply R operator. Well, of course, we're going to write it as phi R phi. But if you want to write it in general, this is with the integral from minus infinity to infinity, integral from minus infinity to infinity, integral from minus infinity to infinity in 3 dimensions, dx, dy, dz, phi x, y, z, which is a normalized state, r phi x, y, z. To calculate these integrals can be difficult, can be not so. Here it's trivial, so I do trivial things. But this is what it means, and you see this is very similar to 1 dimension. You just have to get used to it a little bit and think about it, read, etc. This is not your problem, believe me. You have other problems. Okay, so now let us gain some new insight, a slightly new insight. Let us look at this system when it has full symmetry. What do I mean by full symmetry? What is the full symmetry? What do I mean by that? Let us consider.
A equals B equals C.
Yes. A equal B equal C. אומרים תיבה באנגלית, פתאום ברח לי. In a cube, of course. So this is a cube. It's a perfect cube. All sizes are the same. And I'm going to look at the energy, which is A, Nx, Ny, and Z. The 3 contour numbers are still there. And you see here I have A squared, B squared, and C squared. Okay, now everything is A, so I can write it as H, 8m, H squared, A squared, and here I have Nx squared, and Y squared, plus nz squared. Fine. Now let us look at the energy levels of this cube. Let us say I'm an experimentalist. I prepare this perfect cube, and I want to measure the energy levels. What are the energy levels that I will see? So first of all, the energy levels have a natural unit. So I will actually look at 8ma squared times E over h bar. This is dimensionless, and not h bar, h squared. Okay? So this is simply equal nx squared, ny squared, and z squared. It's super simple. So let us write this quantity starting from 0. What is the, I'm going to write the states. What is the lowest lying energy level? 111. Which means nx equal 1 and y equal 1. I told you the answer is either 1 or 0. 111. And what is the energy in these units? 1 squared plus 1 squared plus 1 squared. That is 3. Well, my scale will not work. What is the degeneracy here? 1. There is only one state corresponding to the ground state. That's the lowest energy. And actually, it's like a sine to all 3 dimensions, because there's no zeros of the wave function. It's like in this direction, it looks like that.
So that's the ground state.
No, this is the ground state. Now, what is the next level? Well, it can be 2, 1, 1. It can be 1, 2, 1. Or it can be 1, 1, 2. The degeneracy here is 3 because you have 3 states. And what is the energy? Well, 2 squared is 4, 1, 1, this is going to be 6. I don't like my scale because, so let me write it a bit. I hope you left enough space in your notebooks. So let us write 3 here, and then 6 is roughly here. Oh. So then these guys will have to go downstairs a little bit. So this is 1, 1, 1. Degeneracy 1, here degeneracy 3, here we have 2, 1, 1, and all permutations. What is the next level? Well, here the degeneracy is, I see they are a bit noisy out there, so the next level is going to be 2, 2, 1. And again, 1 can permutate 3 times, permute 3 times, so the degeneracy here is again 3. What is this energy level? Well, it's 4 plus 4 plus 1, it's 9. The distance is 9. So these are the first 3 levels, and they look like the harmonic problem now. Remember, in the one-dimensional case, it was 1, and then it was 4 because it was the square. Here it goes equal distance at the beginning. And then it's going to be easy for you to convince yourself that the next in line, okay, no scale, is going to be 11. 11 is because you get the following, 3, 1, 1. 3, 1, 1, you have 3 squared, that is 9, plus 1 squared plus 1 squared, that is 11. What is the degeneracy here? That is 1.
What about 2, 2, 2?
2, 2, 2, well, you want 2, 2, 2, you'll get it. Where will be 2, 2, 2? It will be 4 plus 4 plus 4. It's a bit higher than this guy, 12. No, this is not 1. This is 3 degeneracy. This is 2, 2, 2. This guy is 1. This degeneracy, you can switch, right? So you have 1, 3, 1, etc. And then what do you get? You have 3 to 1. And all permutations. How many do you have here? You get 6. Because 1, 2, and 3, you have 6 permutations. So here you have 6, and this is 3 squared, that is 9, plus 4, plus 1, that is 14. So essentially, you see that the degeneracy is not so, there's no general pattern. There are states which are non-degenerate because there's only one quantum number. Many of them have 3, and sometimes you get the 6. That's the only options that you have, because also higher levels, because the maximum is 6, then you have either 1 or 3, right? That's the only options that you can have here. To get the degeneracy, unless there's some magic numbers where 2 types of these guys will fall exactly on the same, you can find them out. If they exist here, they don't. Now, we want to ask the following question. Let us look at one degenerate state. Let's say this guy with 3 states. What will happen if I take the box and I perturb it a little bit, which means the following. I have an experimentalist. I tell him, oh, you know, prepare this box exactly its length, its height, and its width exactly of the same size A. But experimentalists, it's easy to say this. In an experiment, to make this such box, well, no one can really make a perfect box. So let's say A is a little bit bigger than B, and B is a little bit bigger than C. What will happen then? What will you see? How do we at all know in an experiment that there is a degenerate state? So what will happen is that these states, 3 states, what will happen to them? So here I have 2 to 1.
They will be a bit different?
Yeah, they will be a bit different. These are perfect box. This is a perfect cube. If the sizes are a little bit different, then you'll have here a squared, here b squared, and here c squared. Both of the, all of them are a squared, a plus some delta, b, c, a plus some delta, another delta. You expand it, and then you'll get, in the experiment, you'll see a small splitting of these three energy levels. And this means the following. How do we explore degeneracy in the laboratory? We have some symmetry of the system, and we perturb it slightly. Here we perturb it by making the box bigger, but you can perturb it by many other ways. Apply a small magnetic field or an electric field in one direction. Then you remove the degeneracy, and then you see, and then if you can control it, let's imagine that we can control a little bit the size of the box. So I can play with this size. I can make it disappear. When I make it a perfect one, made in China, it will be like this. If it's in Israel, then okay, not so good. You will see the degeneracy. It depends how good the experimentalist is, and of course, how good your measurement device is. Because if you have a small splitting here, it might be very difficult in a measurement to see it. So any imperfections removes the degeneracy, and this is how we can at all define degeneracy. We find it in the theory, and then we perturb the system a little bit, we remove the degeneracy. And what is that? What is exactly removing degeneracy? It's breaking the symmetry of the system. The degeneracy was created because the boxes have same sizes in all the three dimensions. You break the symmetry by making something not perfect, and then you see the breaking of the degeneracy and the splitting. This is how you can measure these things. You can explore degeneracy. Ideally, you can control it. You can make these guys come closer or further away in real laboratory. And this is how we know that degeneracy actually exists. It's not just, because you can ask, okay, you have this energy level. It is degenerate. How do you know that it is degenerate? You know it by breaking the symmetry and then measuring. That's the general answer. Of course, you also know it from theory, but that's not a proof because the theory can be wrong. Okay, so here we will end. I ask you again to start reading on operators, especially the Laplacian in 3 dimensions, the orbital angular momentum, because this is what we are going to study in next lesson, and I'll see you next week. I believe that tomorrow there's no lesson. You know this? You know this. Okay, good. Okay, so enjoy your weekend.